Good day and a warm welcome from the BIOGRIP node at Stellenbosch University. Today, our presenter Volante Moonsamy will be giving a talk on the introduction to total organic carbon analysis. The workshop will cover the following topics: an introduction to TOC analysis, the principles of TOC analyzers, methodology of TOC analysis, importance of TOC analyzers, applications of TOC analyzers, sample preparation involved in TOC analysis, and how to submit your samples for TOC analysis. So, what is carbon? Carbon is the fourth most abundant element on Earth. All life comprises of carbon, and it circulates through the land, ocean, and the atmosphere in a process known as the carbon cycle. The carbon cycle can be further divided into the geological carbon cycle and the biological carbon cycle to create both inorganic and organic carbon. Inorganic carbon is extracted from ores and minerals. Inorganic compounds include calcium carbonate, graphite, and carbon dioxide. Organic carbon is isolated from living organisms and include compounds such as alcohols, methane, sugar, and DNA. What is total organic carbon? TOC is a common acronym for total oxidizable carbon, also referred to as total organic carbon. Total organic carbon is the measure of the level of organic molecules or contaminants in water. In the pharmaceutical industry, TOC is an analytical technique that helps determine whether the water used in their processes are pure. However, all water contains carbon to a certain degree, and sources of water contamination may include natural or altered products of living systems or man-made and synthetic compounds. TOC can be measured both online and offline. Offline methods typically include routine laboratory methods or high concentrations of TOC. Online methods make use of TOC analyzers and are typically used for lower concentrations of TOC. Online methods also have a quicker response time when compared to routine laboratory methods. What do TOC analyzers measure? TOC analyzers measure total carbon and total inorganic carbon, and the total organic carbon is then measured by difference, where the total inorganic carbon is subtracted from the total carbon. Total organic carbon comprises of purgeable organic carbon and non-purgeable organic carbon. Purgeable organic carbon includes volatiles, whereas non-purgeable organic carbon includes the organic carbon and that remains after acidifying a sample below the pH of 3 and purging the sample with air or nitrogen. Non-purgeable organic carbon then comprises of dissolved organic carbon if the sample has been filtered. What are the components of TOC analyzers? There are three parts to TOC analysis, which includes sampling, oxidation, and detection. It is recommended that TOC analyzers should be fitted with an automatic sampling system, perform automatic acidification of samples for the removal of the TIC component, and have the ability to sparge samples with the recommended gas. TOC analyzers should also perform auto-calibrations using a single stock standard for better reproducibility and increased throughput. For the analysis of TOC, organic carbons must be oxidized. Therefore, in the presence of oxygen and a catalyst, total carbon is converted to carbon dioxide and water. There are several types of oxidation methods available. These methods, which can convert total carbon to carbon dioxide, include photocatalytic oxidation, chemical oxidation, high-temperature combustion. Photocatalytic oxidation converts organics to carbon dioxide and water in the presence of UV light and a catalyst, which is usually titanium dioxide. Chemical oxidation mixes a sample with persulfate in a UV irradiated chamber to convert organics to carbon dioxide and water. High temperature combustion mixes a sample with an oxidation catalyst, which is usually 1% platinum or copper oxide, in a chamber heated to 850 degrees or 950 degrees Celsius to convert organics to carbon dioxide and water. TOC analyzers use two types of detectors. These detectors include conductivity detectors with direct measurement or with a membrane filter, and non-dispersive infrared detectors. The conductivity method measures the conductivity of the sample before and after it has been oxidized. The resulting differential measurement is quantified as the TOC in the sample. Briefly, how the direct method works is when the sample is being oxidized, carbon dioxide and other gases are formed. The dissolved carbon dioxide forms a weak acid which changes the conductivity of the original sample in proportion to the TOC content. However, this method is only successful if only carbon dioxide gas is present in the sample matrix. Therefore, membrane conductivity was introduced, which uses a hydrophobic gas permeation membrane. This membrane allows carbon dioxide gas to pass and retains the other gases. NDIR detectors use infrared energy to detect the presence of carbon dioxide. An infrared beam is transmitted through the sample chamber as the sample gas containing carbon dioxide fills the chamber. When the infrared energy passes through the carbon dioxide gas, it creates a unique absorption spectrum, making carbon dioxide distinguishable from other gases, which correlates to the TOC content in the sample. NDI detectors are more popular due to their stability, whereas conductivity detectors has interference issues from other gases, such as chlorine dioxide, sulfur dioxide, and other noxious gases. At the BIOGRIP node, we are equipped with an Elementa Vario TOC cube, which uses high temperature catalytic combustion coupled to a NDIR detector for the detection of total organic carbon, non-purgeable organic carbon, total carbon, and total inorganic carbon. The Elementa Vario TOC cube can operate in both liquid and solid mode. In liquid mode, the TOC analyzer is equipped with a 50-position carousel, and in solid mode, the TOC analyzer is equipped with an 80-position carousel. This is the front view of the internal components in the Vario TOC cube. It contains a 5 ml syringe for dispensing of samples, a multi-way valve to transport samples into the combustion tube, a furnace that holds the combustion tube at a constant temperature of 850 degrees Celsius in liquid mode and 950 degrees Celsius in solid mode, an acid reservoir to hold 1% phosphoric acid, a halogen scrubber which is filled with brass wool to absorb halogens from the sample, and a drying tube which is filled with Aquatac to absorb water vapors. This is the left side of the instrument. The internal components on this side of the instrument include an acid sparger that separates TIC from TC by acidifying the sample with phosphoric acid and purging with synthetic air. It also contains a condenser that separates water from the measuring gas, and the NDI detector, which measures the carbon dioxide gas coming from the sample. These are the combustion tubes which fit into the furnace. The combustion tube in the liquid mode contains the following components: a protective sheath, an ash crucible, quartz wool, quartz chips, and 1% platinum catalyst. In the solid mode, the combustion tube components are the same as in liquid mode. However, the catalyst is copper oxide. During the analysis in liquid mode, the sample is injected directly into the combustion reactor, heated at 850 degrees Celsius via the multi-wave valve. The sample undergoes oxidative combustion in the presence of 1% platinum to convert total carbon to carbon dioxide and water. Thereafter, carbon dioxide gas is transferred to the NDI detector via the synthetic stream, and the carbon dioxide content is quantified as total carbon. The next step involves the acidification of the sample with 1% phosphoric acid in the acid sparger to a pH below 2, and the carbon dioxide gas is released into the condenser. The release of the carbon dioxide gas content is measured by the NDIR detector and quantified as total inorganic carbon. The total organic carbon is then measured by the difference between the total carbon and the total inorganic carbon. During the analysis in solid mode, the sample is dropped into the combustion tube heated at 950 degrees Celsius and undergoes oxidative combustion in the presence of copper oxide to form carbon dioxide and water. The carbon dioxide gas is then transferred to the NDIR detector via the synthetic airstream to measure total carbon. The TOC content can also be measured in solid mode. However, samples would need to be externally acidified with 20 microliter concentrated hydrochloric acid to remove the TIC component. Thereafter, samples need to be dried at 60 degrees Celsius overnight. The TIC component is calculated by difference where the TOC content is subtracted from the TC content. Sample preparation for TOC analysis. In liquid mode, 10 mol sample is dispensed in 12 mol vials and analyzed in triplicates for TOC analysis. In solid mode, an appropriate amount of sample is weighed into silver boats, acidified and wrapped in tin cups for TOC analysis. Preparation of stannates. Liquid stannates are prepared using ultra-pure type 1 water with a TOC content less than 5 ppb. All stannates are prepared as stock solutions of 1000 mg per liter TOC and TIC and serially diluted to 100, 10, and 1 mg per liter to set up different calibration ranges, since this improves accuracy. Stock solutions are prepared with potassium hydrogen phthalate as the organic carbon content and sodium carbonate as the inorganic carbon content. In solid mode, the stannate is a low organic content soil stannate with a carbon percentage of 1.86 weight over weight. How to determine the theoretical carbon content? To calculate the theoretical carbon content, the following parameters should be known: the molecular formula of the compound, the molecular weight of the compound, and the number of carbon atoms in the compound. For example, potassium hydrogen phthalate, also known as KHP, has a molecular weight of 204.22 gram per mole and contains 8 carbon atoms. Therefore, determine the carbon mass per mole by multiplying the number of carbon atoms by the atomic weight of carbon. In this case, the carbon mass per mole in KHP is 96 gram per mole. Then determine the carbon mass portion of KHP by dividing the carbon mass per mole of KHP by the molecular weight of KHP to get a ratio. So to make 8000 mg per liter stock solution of TOC using KHP, you would divide 8000 mg per liter by the carbon ratio. Therefore, add 2127.66 mg of KHP to 1 liter water to make a stock solution of 1000 mg per liter TOC. As mentioned earlier, the TOC analyzer at the BIOGRIP node can perform in both liquid and solid mode. Therefore, a wide array of sample matrices can be analyzed, which include, but are not limited to, drinking water, wastewater, sludge, seawater, microbial biomass, and sand. Marine TOC is important across various industries and generally fall into two categories of process or regulatory control. Marine TOC in municipal drinking water is especially important since organic carbon reacts with disinfection chemicals such as chlorine and forms byproducts which may be carcinogenic. Pure water free of TOC is required to produce drugs in the pharmaceutical industry, since organic carbon is a substrate for growth of harmful microorganisms. Monitoring TOC of municipal wastewater is important for industries which discharge liquid waste into surface waters, since organic carbon serves as a substrate for the growth of pathogenic bacteria. TOC analysis in power plants is important since the potential sources of corrosive compounds can be tracked and limited. This then prevents costly damage to expensive equipment. Aside from having applications in the pharmaceutical and water supply industries, TOC analyzers can be used for the following applications: for the determination of the TOC content in algal biomass, fermentation fluids, and the water used to produce beverages. TOC analysis can also be used to determine the amount of carbon dioxide in beer, for monitoring microbial growth, and for cleaning validation in the food industry. So, where can I send my samples for TOC analysis? TOC analysis can be performed at the BIOGRIP node for soil and water analysis, which is situated at Stellenbosch University in the Western Cape. The BIOGRIP node houses various high-end analytical equipment, amongst which is the Elementa Vario TOC cube, which is capable of measuring the carbon content in both liquid and solid samples. A link to the website is provided. For TOC analysis, sample preparation is required. In liquid mode, a sample size of 50 ml is required. If your sample contains particles, the particle size should be less than 0.5 millimeters to prevent clogging of the sample transfer line. If dissolved organic carbon is required, samples should be filtered with a carbon-free syringe filter with a pore size of 0.45 micron and compatible with your sample type. In solid mode, a sample size of 1 gram is required. Samples need to be dried and milled to a fine powder. The drying temperature is dependent on your sample type. Please label samples according to a sample submission template. Indicate the sample type. Liquid samples can be stored at 4 degrees for 48 hours prior to analysis. Solid samples can be stored in a desiccator prior to analysis. A sample submission template is required for TOC analysis. Please indicate your details in the blocks highlighted in red. Indicate sample ID, it should be unique and not duplicated. Indicate sample types, whether solid or liquid mode is required, and the parameter, for example, TC, TOC, or TIC. For more information on TOC analysis, please contact Dr. Janine Colleen or myself, Volante Moonsamy, on our provided email addresses. Thank you for attending this presentation. Please feel free to contact me for further information.